Hello, and welcome to Bedside Physics. Before we dive into the wonders of the cosmos, don't forget to like, subscribe, and hit that notification bell so you never miss an exploration into the mysteries of the universe. Now, I'd love to hear from you. Where are you watching or listening from? Whether you're tuning in from Earth's bustling cities, or perhaps a more serene corner of the world, it's fascinating to think about how, just like you, we're all connected by the vast and ever-expanding cosmos. In today's journey, we'll be exploring the Big Bang and the birth of the universe. From the tiniest quantum fluctuations to the birth of time itself, we'll unravel the incredible story of how the universe began. The questions we'll address are as old as humanity's curiosity. What happened before the Big Bang? How did time, space, and matter come into existence? And could there be other universes out there, waiting to be discovered? So sit back, relax, and let's venture together into the far reaches of space and time, where the cosmos itself was born. Whether you're here to drift off into a deep sleep, or simply to explore the wonders of our universe, this journey promises to be as awe-inspiring as the universe itself. Let's begin. Before the universe as we know it began, there was no time, no space, no matter. What we often think of as before the Big Bang is actually a concept we struggle to understand, because the very idea of time may not have existed in the way we experience it now. The universe, as we understand it today, emerged from something entirely different, a quantum state beyond time. One theory that has captivated physicists is the idea of a multiverse. The multiverse theory suggests that our universe could simply be one of many, each with its own set of physical laws and properties. This idea introduces the possibility that there was never just one Big Bang, but rather a continuous cycle of births and rebirths, creating an infinite number of universes. This idea was popularized by physicist André Linde, who proposed that quantum fluctuations, tiny random disturbances in the fabric of space-time, could have led to the creation of not just our universe, but countless others. According to Linde's chaotic inflation theory, these fluctuations could have sparked the rapid expansion of the universe, and in some cases might have created entirely new, independent universes. Imagine a vast cosmic foam, with each bubble representing a different universe, each expanding and evolving in its own way. But before we get too carried away with the idea of multiple universes, let's take a step back and consider a more cyclic view of the universe's origins. In the 1960s, British physicist Roger Penrose proposed a fascinating theory called aeons. According to Penrose, the universe goes through an infinite cycle of expansions and contractions, with each Big Bang marking the beginning of a new cycle, or aeon. In this view, the universe we live in is just the latest in an endless chain of universes that have come before and will come after. So, if Penrose's theory is correct, our universe was born out of a previous collapse, a big crunch, where the universe shrank back into a singularity before exploding outward once more. Another intriguing idea about the origin of time itself comes from the work of James Hartle and Stephen Hawking. Together, they proposed the no-boundary condition in 1983. Their theory suggests that time, as we know it, may not have had a beginning in the traditional sense. Instead, they envisioned the universe as a closed surface, similar to the surface of a sphere, where the boundary of time simply disappears as we approach the Big Bang. In this model, time doesn't start in the way we think of it. It just is, without a defined beginning or edge. It's a bit like the question of whether the Earth has an edge. There's no true start or end, just a continuous, seamless unfolding. If Hartley and Hawking are right, then the universe may not have a before at all, at least not in the way we typically understand it. Then there's the idea of cosmological natural selection, put forth by Lee Smolin in 2001. This theory is as fascinating as it is mind-boggling. Smolin proposed that the birth of new universes might not be random at all. Instead, new universes could emerge from the collapse of black holes in our own universe. These new universes would carry the physical laws of the universe from which they originated, but could evolve with slightly different properties over time. This process of natural selection could mean that the universes that are best suited for forming black holes would be the ones that survive and continue to evolve, while those that aren't as fit would simply fade away. In this view, our universe could be the product of a long line of universes, each one more finely tuned for the creation of black holes than the last. This theory might sound like science fiction, but it raises interesting questions about the nature of black holes and the forces that drive the creation of new universes. All of these ideas share a common thread. The universe, in all its complexity, may not be a one-time event, but rather part of an ongoing, evolving process that stretches across an unimaginable scale of time and space. Whether we're talking about quantum fluctuations, the endless cycles proposed by Penrose, the no-boundary condition, or Smolin's cosmological natural selection, what we're really talking about is the possibility that the universe's origins might not be as simple as a single, isolated event. Instead, the Big Bang might just be the latest chapter in an ongoing cosmic story, one that stretches beyond the boundaries of our own understanding. So, when we look at the Big Bang, we aren't just gazing at the birth of our own universe. We might be looking at a small piece of a much larger, more complex picture, one where the boundaries of time and space are far more fluid than we could ever have imagined. Each theory offers a different lens through which we can view the cosmos, inviting us to rethink what it means for something to begin, or even to exist. The universe, it seems, may have a story much longer and far stranger than we can yet comprehend. The very first moments of the universe were a time of pure chaos, where the laws of physics as we understand them today didn't quite apply. During the first 10 to the power of negative 43 seconds after the Big Bang, often referred to as the Planck time, space-time was so small and so turbulent that quantum mechanics was in complete control. It was a time when our usual ways of thinking about space and time simply couldn't keep up with the extraordinary conditions of the early universe. At this incredibly brief instant, quantum fluctuations, which are tiny random changes in energy, dominated the scene. This is the domain where the weirdness of quantum mechanics becomes incredibly important. It's here, in this tiny fraction of a second, that the universe's potential was planted, before any of the particles we recognize today had even formed. One of the key theories that tries to explain what happened in this tiny window of time is called loop quantum gravity. This theory, proposed by physicist Carlo Rovelli and others, suggests that space-time itself is quantized at the smallest scales. That means, just like matter and energy come in discrete packets, space and time also come in small, indivisible units at the Planck scale. In other words, the smooth fabric of space-time that we experience in our everyday lives is an illusion at the smallest scales. Instead, space-time is more like a finely woven fabric, made up of tiny loops and threads, each too small for us to see but still having a profound effect on how everything behaves. In loop quantum gravity, the idea of space and time being continuous breaks down. Instead, space-time becomes granular, almost pixelated in this incredibly small region of the universe. This is one way of reconciling quantum mechanics with the theory of general relativity, which describes the large-scale behavior of space-time. When we combine the two, at the Planck scale, this quantization of space-time is what helps keep the universe from collapsing into an infinite point, offering a possible solution to the so-called singularity problem that exists in traditional models of the Big Bang. But not all scientists agree on this point. There's another fascinating theory that offers an entirely different view of how the universe began, one that's cyclical rather than originating from a singularity. This is the ekpyrotic universe model, proposed by cosmologists Paul Steinhardt and Neil Turok in the late 1990s. In their theory, the Big Bang was not the beginning of everything. Instead, the birth of our universe came from the collision of two higher dimensional branes, membranes of space-time that exist within a higher dimensional space. These branes are essentially parallel universes that can collide and bounce off one another in a way that could create a new universe each time. Think of these branes as sheets of paper, floating in a higher dimensional space, each one carrying its own universe. Over time, they approach each other, and when they finally collide, it creates an enormous release of energy, the Big Bang. This collision sparks the creation of an entirely new universe, while the previous one is essentially wiped out or transformed. The ekpyrotic model presents the universe as part of an ongoing cycle, where the Big Bang we experienced is just one in a long series of expansions and contractions, driven by the interactions between these branes. This theory challenges our traditional understanding of the universe's beginning, suggesting that time and space might be infinitely cyclic, with each universe emerging from the previous one. This cycle of expansion and contraction doesn't just happen once, it could continue indefinitely, offering a far more complex and dynamic picture of cosmic evolution than the idea of a singular origin. Then, there are even more speculative theories about the very nature of time itself during this era. If we look at time as a continuous flowing river, the Planck era was more like the point where the river begins, a moment so close to the origin that it becomes difficult to speak meaningfully of time at all. This is where physicists like Julian Barbour and Paul Davies come in. They've suggested that perhaps time itself didn't exist before the Big Bang, at least not in the way we experience it now. Barbour, for instance, proposes that time may be an illusion, something that only emerges at a certain level of complexity. According to his view, the universe doesn't have a beginning or end in the traditional sense. Instead, everything that exists is part of an eternal, timeless whole, where the flow of time is an emergent property that comes into play as the universe evolves. In this view, the universe doesn't start from a point in time. Time itself simply begins as the universe transitions into a state of greater complexity. Similarly, Paul Davies has proposed the idea of a timeless pre-Big Bang universe. He suggests that before the Big Bang there was no definite boundary between time and space. Instead, time itself may have been a property that only emerged as the universe began its rapid expansion. In this model, the idea of a before the Big Bang doesn't really apply. There was no time to speak of before the moment of creation. What's even more intriguing about these ideas is that they push the limits of our understanding of not just the universe's origin, but of reality itself. If time as we know it was born with the Big Bang, then what does that mean for the universe before that moment? Does time truly have no beginning, as Barbour and Davies suggest? Or was there something even more fundamental, an aspect of reality that we simply haven't yet discovered? Of course, these theories remain speculative, and there is much debate within the scientific community about which, if any, of these ideas are correct. The Planck era, this infinitesimally small sliver of time where quantum mechanics reigns supreme, is still a mysterious frontier in our understanding of the universe. But by exploring these different theories, from the quantized spacetime of loop quantum gravity to the cyclical models proposed by Steinhardt and Turok, to the more speculative ideas of a timeless universe, we begin to realize just how little we truly know about the universe's origins. The Planck era is a place where the known laws of physics break down, and new uncharted theories take center stage. It's a time that challenges everything we thought we understood about space, time, and reality itself. And although we may not yet have all the answers, the journey to understand this period, where the quantum and cosmological realms collide, offers one of the most exciting frontiers in modern physics. At the moment the universe began, time itself emerged, but the question of how time could possibly begin is one of the deepest mysteries of cosmology. In fact, before the Big Bang, the very concept of time might not have even existed in the way we understand it now. Instead, what we see as time may have been a result of quantum processes that took place in the early universe. To understand how time emerged from the quantum vacuum, we first need to grasp what the quantum vacuum actually is. The quantum vacuum is not an empty void, as the name might suggest. Rather, it's a seething dynamic field where particles pop in and out of existence. This is a key concept in quantum field theory, which underpins much of modern physics. The vacuum is not devoid of activity. It is alive with fluctuations, like a calm ocean surface constantly rippling with tiny waves, even when there is no wind. Edward Witten, one of the leading figures in theoretical physics, helped refine our understanding of this quantum vacuum. In his work on string theory, Witten explained how the vacuum state could act as a source of energy, an energy that would eventually give rise to the Big Bang itself. Witten's work builds on the idea that, even in a vacuum, there are constant fluctuations in energy and fields, and these fluctuations can provide the spark necessary for the universe to begin. According to this theory, the quantum vacuum could have been the very birthplace of space-time as we know it. One of the most famous theories that expands on this idea is the theory of inflation, first proposed by physicist Alan Guth in 1981. Guth's work on vacuum energy and cosmic inflation revolutionized our understanding of the early universe. According to Guth, the universe underwent an incredibly rapid expansion during its first moments, so rapid that it increased in size by a factor of at least 1 trillion times in a fraction of a second. This expansion was driven by a type of energy present in the quantum vacuum, vacuum energy. In simple terms, Vacuum energy is the energy that exists in empty space, a sort of dark energy that was fueling the rapid inflation of the universe. This energy came from quantum fluctuations in the vacuum itself. As the universe expanded, these fluctuations stretched out and created the very fabric of space-time. The rapid inflationary phase set the stage for the universe's later growth and development, allowing the particles that eventually formed atoms, stars, and galaxies to exist. Now, let's consider the way space-time itself behaved during the early universe. John Wheeler, a physicist famous for his contributions to general relativity, introduced a concept that has become one of the most mind-boggling ideas in modern cosmology: quantum foam. Wheeler suggested that, at incredibly small scales, space-time is not smooth and continuous, but instead is a frothy, turbulent foam. At the Planck scale, the scale where the effects of quantum mechanics and gravity both become important, space-time itself becomes a chaotic, fluctuating structure. This quantum foam is often described as a sea of constantly changing, fluctuating space-time bubbles that pop in and out of existence. It's a bit like imagining the surface of the ocean, where waves and ripples constantly shift and change. Only in this case, it's the fabric of space-time itself that is in constant motion. This idea suggests that, at the smallest scales, space and time are not smooth and predictable, but instead behave in a very chaotic, random way. It's a highly speculative but deeply intriguing concept that challenges our usual notions of space and time. These fluctuations in space-time may have played a role in the birth of time itself. If time did not exist as a continuous flow before the Big Bang, then how did it come into being? Paul Davies, a physicist known for his work in cosmology, proposed a theory that attempts to address this very question. He suggested that, before the Big Bang, there was no time in the way we know it. Instead, time itself emerged with the Big Bang. In this model, the idea of before the Big Bang is meaningless, because time itself began at that moment. According to Davies, if the Big Bang marked the beginning of time, then there was no time prior to it, no before to speak of. This theory suggests that time didn't stretch infinitely backward, but instead began with the creation of the universe itself. If this theory holds, it challenges our deepest intuitions about the nature of time, suggesting that the flow of time is not something that has always existed, but rather something that emerged at a very specific moment in history. Julian Barbour, a theoretical physicist, took this idea even further with his theory of a cyclical universe. Barbour proposed that time itself may not be linear, as we traditionally think of it, but instead may be cyclical. In this model, the universe goes through endless cycles of creation and destruction, with each cycle representing a new Big Bang and a new beginning. For Barbour, time doesn't flow in one direction from the past into the future. Instead, the universe evolves through a series of moments, or configurations, where each moment is independent of the others. In this view, time itself is not a continuous stream, but rather a series of individual now moments that come and go, each marking the birth of a new universe. Barbour's cyclical model suggests that time could be something much more fluid than the linear, irreversible flow that we experience in our everyday lives. Instead of time always moving forward, it could be cyclical, with each universe experiencing its own time, independent of the others. This raises fascinating questions about the nature of time itself. If time is cyclical, what happens when a universe ends? Does time simply reset, only to begin again with a new cycle, or is there some sort of transition between these moments? These questions continue to intrigue physicists as they seek to understand not just how the universe began, but how time itself might work at the deepest levels. These different theories, the quantum vacuum, the nature of space-time as quantum foam, the emergence of time with the Big Bang, and the idea of a cyclical universe, all offer fascinating perspectives on one of the most profound questions in cosmology. Where did time come from, and how does it fit into the fabric of the universe? Perhaps the most intriguing aspect of these theories is that they challenge the very foundations of what we think we know about the universe. Time, once thought to be a simple linear progression from past to future, may be far more mysterious and complicated than we could have imagined. The interplay between quantum mechanics, the structure of space-time, and the birth of the universe has opened new doors of understanding, and yet we're only beginning to scratch the surface of these mysteries. In the earliest moments of the universe, a theory emerged that would completely reshape how we think about the cosmos. a theory that proposes the universe expanded at an incredible rate, far faster than anything we could ever observe today. This theory is known as inflation, and it offers a profound explanation for the smooth, uniform nature of the universe we see now. Inflationary theory was first proposed by Alan Guth in 1981, but it has since evolved into a far more complex and fascinating framework. The basic idea of inflation is simple. The universe, in its first moments, expanded exponentially in size, much faster than the speed of light. So fast, in fact, that it expanded by a factor of at least 1 trillion times in a fraction of a second. This rapid expansion helped to explain why the universe, on large scales, looks so homogeneous and isotropic, meaning it appears roughly the same in every direction. But the story doesn't end with the original concept of inflation. In the decades following Guth's proposal, many physicists began to build on this idea, adding layers of complexity that would completely change how we think about the universe's origins. One of the most important additions to inflationary theory is the concept of eternal inflation. This idea, first explored by Andre Linde, suggests that inflation might not have stopped after the birth of our universe. Instead, it could continue indefinitely in some regions of space-time, creating new pocket or bubble universes within a vast multiverse. To understand this idea, imagine a vast inflating balloon, where some regions of space-time stop inflating and form new universes, while others continue to expand uncontrollably. These new universes are like bubbles in a pot of boiling water, each expanding and evolving in its own way. Our universe, according to eternal inflation, would simply be one of many bubbles, each with its own unique set of physical laws. In this model, inflation never truly ends. Instead, it continues forever in some parts of the universe, creating a vast, sprawling multiverse. But how exactly did our universe come into being in this scenario? This is where the concept of chaotic inflation comes in, introduced by Linde in 1983. According to chaotic inflation, our universe began as a tiny quantum fluctuation in the fabric of space-time. This fluctuation, caused by the inherent randomness of quantum mechanics, triggered a rapid inflationary burst, expanding the universe from a microscopic point to something much larger and more familiar. In the chaotic inflation model, the universe begins as a quantum fluctuation, a small temporary disturbance in the quantum vacuum. This fluctuation was enough to spark the rapid expansion that gave birth to the universe as we know it. But what's particularly fascinating about this model is the idea that it could be one of many such fluctuations, each creating a new universe. In fact, the universe that we live in could just be one bubble in a much larger cosmic foam, with each bubble having its own set of physical laws and properties. This leads us to the concept of bubble universes, an idea that is central to the multiverse theory. The multiverse suggests that our universe is just one of an infinite number of universes that exist simultaneously, each created by its own inflationary event. The work of physicists like David Deutsch and others has proposed that these bubble universes could be connected in ways that we can't yet understand, but they represent a fundamental part of how the universe evolves. According to this theory, the Big Bang we experienced may have simply been the birth of our universe, a single bubble in a much larger multiverse that continues to expand. But how does dark energy fit into all of this? Robert Wald, a respected physicist, has proposed that dark energy, the mysterious force causing the universe to expand at an accelerating rate, might play a crucial role in continuing inflation. Dark energy is believed to make up about 70% of the universe's total energy content, and its influence has been growing stronger over time. Wald's theories suggest that the energy from dark energy could be driving the continued expansion of the universe, potentially fueling eternal inflation. If Wald's ideas are correct, the role of dark energy in the ongoing expansion of the universe could be even more significant than we realize. Dark energy may not only explain the current acceleration of the universe, but could also be the key driver in creating new universes, allowing inflation to continue in regions of space-time far beyond our own universe. This would mean that the universe we know is part of an ever-expanding, ever-growing multiverse, where each universe is born from the same process of inflation, but with different properties and physical laws. These ideas may sound mind-boggling, but they offer some powerful explanations for why the universe looks the way it does. For example, one of the key predictions of inflation is that the universe should be extremely homogeneous. with temperature differences between distant parts of the universe being very small. This idea fits perfectly with observations made by the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation shows that the universe, on large scales, is remarkably uniform, with only slight variations in temperature, exactly as inflation predicts. Of course, these theories, especially the multiverse and eternal inflation, are still speculative. There is no direct evidence yet that other universes exist, or that inflation continues in distant regions of space, but these ideas offer a framework that helps explain some of the most puzzling questions about the universe, such as why it is so uniform and why it is expanding at an accelerating rate. The implications of eternal inflation are profound. If the multiverse theory is correct, it means that our universe is just one of an infinite number of universes, each with its own history and physical laws. The possibility of an infinite number of universes raises deep philosophical and scientific questions about our place in the cosmos. Are we truly unique, or are we just one of many universes that happen to support life? And if our universe is part of a larger multiverse, what does that say about the fundamental nature of reality itself? The idea of eternal inflation also challenges our understanding of the beginning of time. If inflation continues indefinitely, then there is no clear beginning of time. Instead, time could be part of an eternal process, with universes constantly being born from the fabric of space-time. In this view, the Big Bang we experienced may have been just one moment in an endless sequence of cosmic births and rebirths. These theories, while speculative, help to stretch the boundaries of our imagination and challenge us to think bigger and more boldly about the universe. As we continue to probe the mysteries of space-time and the forces that shape the cosmos, we may one day uncover new evidence that confirms or refines these ideas. But for now, these concepts, eternal inflation, chaotic inflation, and the multiverse, give us a glimpse into a much larger and more intricate cosmos than we could ever have imagined. The early universe was an intensely chaotic place, where quantum mechanics and the fundamental forces of nature were tightly interwoven. It was here, in this minuscule fraction of time after the Big Bang, that the very structure of the universe began to take shape, well before galaxies, stars, and planets could emerge. The task of understanding this formation goes beyond the standard model of particle physics, which accounts for most of the particles and forces we observe today. To understand how the universe formed at its most fundamental level, we need to consider ideas and theories that challenge and expand the standard model. At the core of the early universe's formation was the role of the fundamental forces, especially the strong force. The strong force is responsible for holding atomic nuclei together, and it was essential in shaping matter in the universe's early stages. This force was first studied in depth by scientists like David Gross and Frank Wilczek, whose groundbreaking work in the 1970s helped establish the theory of quantum chromodynamics, or QCD. QCD describes how quarks, the building blocks of protons and neutrons, interact through the strong force. This force is so powerful that it holds the atomic nucleus together despite the repulsive electromagnetic force that tries to push positively charged particles apart. In the early universe, when temperatures and densities were incredibly high, the strong force played a critical role in the formation of matter. As the universe cooled and quarks and gluons, the particles that mediate the strong force, combined, they formed protons, neutrons, and eventually atomic nuclei. This process was key to the early structure of the universe, allowing matter to form and begin to cool, setting the stage for the creation of atoms and later stars and galaxies. Without the strong force and the insights from Gross and Wilczek, we wouldn't be able to understand the building blocks of matter in the universe today. However, the story doesn't end with the strong force. The early universe is still shrouded in mystery, especially when it comes to understanding the mysterious dark matter that makes up about 25% of the universe. While we know dark matter exerts gravitational influence and plays a crucial role in galaxy formation, its composition remains one of the most intriguing questions in cosmology. One leading candidate for dark matter is a hypothetical particle known as the axion, proposed by physicists Roberto Peccei and Helen Quinn in the 1970s. Axions are incredibly light particles that interact very weakly with ordinary matter, making them difficult to detect. If they exist, they could explain the presence of dark matter, helping to account for the missing mass that we observe in galaxies and galaxy clusters. Axions are also tied to a theoretical problem in particle physics called the strong CP problem, which addresses why the strong force doesn't violate certain symmetries in nature. Pache and Quinn's theory suggests that the axion could be the solution to this problem, and in doing so it may also provide a critical piece in the puzzle of dark matter and the universe's early structure. But the mystery of the early universe doesn't end with the strong force and axions. In order to fully understand the universe's formation, we must also explore the concept of supergravity, a theory that attempts to combine general relativity, the theory of gravity, with the principles of quantum mechanics. Supergravity was proposed in the 1970s by Sergio Ferrara and Peter van Nieuwenhuizen. It suggests that gravity and the other fundamental forces could be described by a more unified framework, where all particles, including the force-carrying ones, are viewed as manifestations of superparticles. In the context of the early universe, supergravity offers a way to understand how gravity could have behaved at high energies during the Big Bang. It suggests that, at very small scales, gravity might behave differently from how we experience it today, helping to explain some of the fundamental mysteries of the early universe. This theory also opens the door to understanding how space-time itself could have emerged from a unified set of forces, a concept that is at the heart of many modern attempts to develop a theory of quantum gravity. While supergravity offers valuable insights into the structure of the universe, one of the most ambitious frameworks for understanding the early universe is string theory, developed by physicists Leonard Susskind and others. String theory proposes that the fundamental building blocks of nature are not point-like particles, but rather tiny vibrating strings of energy. These strings can vibrate in different patterns, giving rise to the various particles and forces we observe in the universe. String theory is a highly speculative but deeply influential idea, suggesting that at the smallest scales, space-time itself is made of these vibrating strings. One of the most fascinating aspects of string theory is its ability to incorporate gravity into the framework of quantum mechanics. This is important because up until now, general relativity and quantum mechanics have been two separate pillars of physics that have never been fully reconciled. String theory, however, holds the promise of unifying them into a single theory of everything, which could explain both the large-scale structure of the universe, described by general relativity, and the behavior of particles at the smallest scales, described by quantum mechanics. If string theory holds true, it could offer a comprehensive explanation for the origin of the universe, the nature of time and space, and the fundamental forces that shape everything around us. While string theory has yet to be experimentally verified, it has had a profound impact on how we think about the universe's structure. It suggests that the universe is far more complex than we could have imagined, with many more dimensions of space-time than the 3 dimensions we experience in our daily lives. In fact, string theory predicts that the universe has as many as 10 dimensions, 9 spatial dimensions and 1 time dimension, though we can only perceive the 3 dimensions of space and 1 dimension of time that we interact with directly. String theory also provides a framework for understanding the conditions that existed in the very early universe, before the formation of matter and the fundamental forces. It offers insight into how the universe could have transitioned from a highly energetic state to the more structured universe we see today. By considering the universe as a collection of tiny vibrating strings, string theory opens up a whole new way of thinking about the origins of the cosmos. As we continue to explore these ideas, strong force, axions, supergravity, and string theory, we see that the early universe was a place of incredible complexity. Matter, energy, and space-time were all intertwined in ways that we are only beginning to understand. The quantum mechanics that govern the smallest scales of nature played a crucial role in shaping the universe, from the formation of the first particles to the birth of galaxies. And as we continue to investigate the quantum origin of structure, we may uncover even more unexpected connections between the forces that govern the universe, revealing a deeper, more unified picture of the cosmos than we ever imagined. The universe's early formation is a realm where physics, imagination, and mystery converge. By exploring the frontiers of particle physics and cosmology, scientists are uncovering the intricate details of how the universe came to be. With each new discovery, we move closer to understanding the profound origins of the structure of the universe and the forces that shaped it. At the very heart of the universe's creation lies a deep mystery, the emergence of matter itself. After the Big Bang, the universe was in an incredibly hot and dense state, a sort of cosmic soup where particles were not yet formed and the entire universe was essentially pure energy. But over time, as the universe cooled, something remarkable happened. Matter began to form. This is where the concept of symmetries, or rather, the breaking of symmetries, plays a key role. In physics, symmetry refers to the idea that certain properties of the universe remain unchanged under specific transformations. For example, the laws of physics are thought to be symmetric under time translation, meaning they remain the same whether you're looking at them now or a million years from now. Similarly, spatial symmetries suggest that the laws of physics are the same everywhere in the universe. But during the early moments of the universe, these symmetries were broken, allowing matter to emerge from the primordial energy. One of the key theories that explain how this happened is known as baryogenesis. The word baryon refers to particles like protons and neutrons, which make up the matter around us. Baryogenesis refers to the process by which matter came into being, specifically in the form of baryons, in the very early universe. One of the key figures in developing the theory of baryogenesis is physicist Michael Turner, who in the 1980s and 90s proposed that a slight imbalance between matter and antimatter could have been responsible for the creation of the matter we observe today. In the early universe, equal amounts of matter and antimatter were produced, but when matter and antimatter meet, they annihilate each other, converting into pure energy. For the universe to have more matter than antimatter, some subtle imbalance must have occurred during the cooling process after the Big Bang. Turner's theories suggested that this imbalance, likely involving the breaking of certain symmetries, led to the excess of matter that we observe today, leaving behind only a small amount of antimatter. But what exactly caused this imbalance? This is where a phenomenon known as CP violation comes in. CP violation refers to the violation of the combined symmetry of charge conjugation, C, and parity, P. In simpler terms, charge conjugation refers to switching particles with their antiparticles, while parity refers to flipping the universe in a mirror. Under normal circumstances, the laws of physics should be symmetric under these transformations, meaning the behavior of particles should be the same if you swapped particles for antiparticles or flipped the universe in a mirror. But in the early universe, this symmetry was broken, and it's this violation that allowed matter to dominate over antimatter. CP violation was first explored in detail by physicists Makoto Kobayashi and Toshihide Masukawa in 1973. They proposed that there could be a fundamental asymmetry in the way quarks, the particles that make up protons and neutrons, interacted with the weak nuclear force. Their theory predicted that, under certain conditions, this asymmetry would lead to a slight imbalance between matter and antimatter. For their work, Kobayashi and Masukawa were awarded the Nobel Prize in Physics in 2008, a recognition of how their theory reshaped our understanding of particle physics and the universe's origins. But CP violation alone isn't enough to fully explain the matter-antimatter imbalance. There are still many unanswered questions about the specific mechanisms that occurred in the first moments after the Big Bang. One speculative idea involves the existence of sterile neutrinos. Sterile neutrinos are a theoretical type of neutrino, a particle that interacts very weakly with normal matter. Unlike the familiar neutrinos, which are involved in weak nuclear interactions, sterile neutrinos are hypothesized to interact only through gravity. These particles, if they exist, could have played a role in the creation of matter by altering the balance between matter and antimatter. While no direct evidence for sterile neutrinos has been found yet, they remain an important and intriguing part of ongoing research into the nature of dark matter and the origins of the universe. The concept of CP violation and its connection to baryogenesis was further developed by physicist A.D. Sakharov, who in the 1960s laid out three key conditions necessary for the generation of an imbalance between matter and antimatter. First, there must be a violation of CP symmetry. Second, there must be a departure from thermal equilibrium, meaning that the universe must have been in a state where processes could occur that would not have been allowed in a balanced state. Third, there must be interactions that would allow baryons, or particles like protons and neutrons, to be produced in greater quantities than antibaryons. These conditions, known as Sakharov's conditions, are still considered fundamental to our understanding of how the universe evolved from a nearly equal mixture of matter and antimatter to the matter-dominated cosmos we see today. Sakharov's work didn't just help to explain the origin of matter, it also led to deeper questions about the fundamental forces that govern the universe. The imbalance between matter and antimatter is linked to the interplay of the weak force, the strong force, and the Higgs field, which gives particles their mass. Each of these forces played a crucial role in shaping the early universe, and understanding how they worked together in the first moments after the Big Bang remains one of the most exciting areas of research in cosmology. But the story doesn't end with the forces and particles we already know about. The universe we see today is not just made of protons, neutrons, and electrons. It's also filled with dark matter, an invisible substance that makes up about 25% of the universe's mass. Dark matter interacts with normal matter only through gravity, which makes it incredibly difficult to detect. But its influence is undeniable, as it shapes the formation of galaxies and clusters of galaxies. And while we still don't know exactly what dark matter is, one of the key ideas being explored is the role of new particles, like axions or sterile neutrinos, in this mysterious form of matter. The hunt for dark matter is ongoing, and scientists are using a variety of methods to search for it, from particle detectors deep underground to observations of the cosmic microwave background radiation. Understanding the origins of dark matter and its role in the evolution of the universe is crucial for fully understanding how the cosmos evolved from a hot, dense soup of particles to the vast structured universe we observe today. The creation of matter in the early universe was a delicate process that involved the breaking of symmetries, the violation of certain laws of physics, and the formation of particles and forces that we are only beginning to understand. From baryogenesis and CP violation to the role of sterile neutrinos and dark matter, the story of how matter emerged from the primordial energy of the Big Bang is still unfolding. What we do know is that the forces at play in the early universe were far more complex than anything we experience today. The universe that we see now, with its galaxies, stars, and planets, was built upon these fundamental processes that took place in the first few moments after the Big Bang, a time when the laws of physics were still coming into existence. As we continue to explore these processes and uncover new details about the universe's origins, we gain a deeper understanding not only of the cosmos, but also of the fundamental forces that govern all of reality. The questions that remain about the nature of dark matter, the origin of the matter-antimatter imbalance, and the interplay between the fundamental forces are some of the most profound challenges in modern science, and they promise to shape our understanding of the universe for generations to come. The universe we know may not be the only one. In fact, one of the most intriguing ideas in modern cosmology is the possibility that our universe is just one of many in a vast, interconnected multiverse. The concept of a multiverse suggests that beyond the Big Bang that gave rise to our universe, there could be an infinite number of other universes, each with its own laws of physics, its own fundamental constants, and potentially its own forms of life. This idea changes the very nature of what we consider the universe, and opens up a whole new set of questions about existence itself. One of the most compelling theories about the multiverse arises from the idea of bubble universes. Imagine for a moment that the cosmos is like a vast expanse filled with countless bubbles, each one representing a different universe. These bubbles are formed through a process called eternal inflation, a key concept introduced by André Linde. According to this theory, the inflationary expansion that we associate with the Big Bang did not stop at the formation of our universe. Instead, it continues in some regions of space-time, creating new bubbles or pocket universes within a much larger multiverse. Each of these universes could have different physical properties, perhaps some with different numbers of dimensions or different constants of nature that govern how particles behave. This bubble universe concept is tied to the idea of brane cosmology, a fascinating theory that arises from string theory. Brane cosmology suggests that our universe is confined to a brane, a higher dimensional object somewhat like a membrane that exists within a larger multidimensional space. The Big Bang, in this view, might have been the result of a collision between two of these higher dimensional branes. Each brane could potentially harbour its own universe, with distinct laws of physics and even different dimensional structures. Our universe, then, could be just one of many branes floating in this vast higher dimensional space, each one with its own Big Bang and its own unique set of properties. This idea of a multiverse, of countless universes, each with different laws and properties, was further developed in the work of physicists like Leonard Susskind. Susskind, in his study of string theory, introduced the concept of the landscape of the multiverse. String theory suggests that at the most fundamental level, the building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings vibrate in many possible ways, and their different vibrational patterns correspond to different particles and forces. The problem is that string theory allows for a vast number of possible solutions, on the order of 10 to the power of 1,000 distinct possibilities, each one representing a different configuration of the universe. This landscape of possible universes is what Susskind referred to as the string theory landscape. If string theory is correct, it suggests that there are a nearly infinite number of possible universes, each with different physical laws depending on how the strings vibrate. Some of these universes might have very similar properties to ours, while others might be drastically different. The landscape offers a framework for understanding why our universe has the properties it does. In a multiverse, we simply happen to live in one of the many possible universes where the conditions happen to support the kind of life we know. The idea of a multiverse also intersects with another fascinating idea known as the anthropic principle. The anthropic principle suggests that the universe we observe is not necessarily typical, but instead it is the way it is because it allows life to exist. In other words, if the fundamental constants of nature, such as the strength of gravity or the mass of elementary particles, were even slightly different, life as we know it would not be possible. The anthropic principle suggests that the reason our universe is so finely tuned for life is simply because we live in it. If the universe were different, we wouldn't be here to observe it. This leads us to a key idea in the multiverse theory. The fine-tuning of our universe may not be a coincidence at all. If there are indeed an infinite number of universes, each with different physical laws, then it makes sense that we would live in one where the conditions are just right for life. The multiverse could provide a natural explanation for why the constants of nature in our universe happen to support life. It's because there are so many universes, each with different properties, that we just happen to live in one of the rare ones where conditions allow life to emerge. Physicist David Deutsch, who has been a key proponent of the multiverse idea, suggests that this perspective has profound implications for our understanding of reality. In a multiverse, our universe is not isolated. It's part of a much larger, ever-expanding cosmic web. Each universe within this web might have its own version of physics, its own history, and its own potential for life. The idea of a multiverse challenges our traditional understanding of reality, suggesting that everything we know might be just one version of a much more expansive and diverse cosmic structure. The idea of multiple universes is certainly mind-boggling, but it is also supported by some of the deepest insights in modern physics. For example, the theory of quantum mechanics suggests that every quantum event can lead to multiple possible outcomes. This leads to the many worlds interpretation of quantum mechanics, first proposed by Hugh Everett III in the 1950s. In this interpretation, each time a quantum event occurs, such as the measurement of a particle, each possible outcome creates a new universe. These parallel universes exist alongside our own, each branching off from different quantum events. In this view, the multiverse is not just a collection of bubbles or brains, it's a vast branching structure created by the fundamental uncertainties of quantum mechanics. But how do we test the idea of a multiverse? It's a difficult question, as the universes within the multiverse may be completely inaccessible to us. If the multiverse is real, the other universes may be separated from ours by vast stretches of space-time, or they may exist in dimensions beyond our ability to perceive. Some scientists, like physicist Raphael Bousso, have proposed ways of testing the multiverse hypothesis by looking for signs of crosstalk between universes. Bousso's work on the landscape of the multiverse suggests that there may be observable consequences of the existence of other universes, even if they are far beyond our reach. For example, the collision of bubble universes or the interaction of brains might leave subtle imprints on the cosmic microwave background radiation, the afterglow of the Big Bang that we could detect. The idea of a multiverse is still highly speculative, and there is no definitive experimental evidence that proves its existence. But it remains one of the most exciting and profound possibilities in cosmology, offering a radically different way of thinking about the universe and our place within it. If the multiverse is real, it suggests that the Big Bang was just one of many, and our universe is part of an endless, ever-expanding web of cosmic creation. The discovery of such a multiverse would not only change our understanding of the cosmos, but also challenge the very nature of reality itself. As we explore these ideas, from the bubble universes of inflationary theory to the many worlds of quantum mechanics, we begin to see a picture of a universe far larger and more intricate than we could ever have imagined. Whether or not the multiverse is real, the theories that suggest its existence have pushed the boundaries of science, inviting us to think in new and exciting ways about the nature of the cosmos and our place in it. The idea that we may be one of many universes, each with its own set of rules, is as exhilarating as it is humbling, and it's a reminder that the universe is full of mysteries, many of which we have yet to uncover. The universe, as we know it, is not entirely composed of the visible matter we can see in stars, galaxies, and planets. In fact, the vast majority of the universe is invisible to our eyes and remains one of the biggest mysteries in modern science. Two key concepts, dark matter and dark energy, are believed to make up approximately 95% of the total energy and matter in the universe, but we cannot directly detect them. Instead, scientists infer their existence based on their effects on the universe's structure and expansion. These invisible forces shape the cosmos in ways we're only beginning to understand. Let's start with dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, making it undetectable through conventional means. Yet, we know it must exist because of its gravitational effects on visible matter. One of the strongest pieces of evidence for dark matter comes from the observation of galaxies and their rotation. If you look at a galaxy, the stars near the edge of the galaxy are moving much faster than would be expected based on the mass we can see. In fact, the stars at the outer edges of galaxies are moving so quickly that they should fly off into space if only the visible matter were responsible for holding them together. However, the galaxies remain intact, suggesting there is additional unseen mass that's exerting gravitational pull. This is the effect of dark matter. One leading candidate for dark matter is something known as WIMPs, which stands for Weakly Interacting Massive Particles. WIMPs are hypothetical particles that are much heavier than protons and neutrons, but interact with ordinary matter only through gravity and the weak nuclear force. This means they're incredibly difficult to detect, since they don't interact with light in any meaningful way. The concept of WIMPs was proposed in the 1990s, and John Ellis, along with other physicists, suggested that these particles could be the key to understanding dark matter. According to this theory, WIMPs could explain the observed gravitational effects on galaxies and galaxy clusters, where the gravitational influence of dark matter is detected even though the matter itself is invisible. Despite extensive searches using detectors deep underground and in space, scientists have yet to directly detect WIMPs, but the theory remains a strong contender. However, not everyone agrees that WIMPs are the answer. There are alternative theories that try to explain the effects attributed to dark matter without invoking invisible particles. One such theory is called Modified Newtonian Dynamics, or MOND. Proposed by Israeli physicist Mordechai Milgram in 1983, MOND suggests that, at very large scales, the laws of gravity behave differently than we expect. According to MOND, the force of gravity weakens more slowly than Newton's laws predict at very low accelerations, such as those found in the outskirts of galaxies. This change in the behavior of gravity could explain the observed galaxy rotation curves without needing to introduce dark matter. While MOND successfully explains many of the same phenomena that dark matter theories do, it's not as widely accepted because it doesn't fit as neatly with the general theory of relativity or with other cosmological observations such as the cosmic microwave background radiation. Nevertheless, MOND remains an interesting alternative that challenges our understanding of gravity and the universe's structure. Despite the mystery surrounding dark matter, there's another invisible force that plays an even more prominent role in the universe: dark energy. While dark matter seems to be holding galaxies together through its gravitational pull, dark energy appears to be doing the opposite, driving the universe apart. In fact, dark energy is thought to be responsible for the accelerated expansion of the universe, a discovery that shocked scientists in the late 1990s. This discovery came from the work of Adam Rees and his team, who were studying distant supernovae to measure the rate of expansion of the universe. They expected to find that the universe was slowing down as gravity pulled matter together. Instead, they found that the universe was expanding faster and faster, suggesting that some unknown force was pushing galaxies apart. This mysterious force was named dark energy, and it now accounts for about 70% of the total energy content of the universe. The nature of dark energy remains one of the greatest unsolved puzzles in cosmology. It is often described as a form of energy that fills empty space and causes the expansion of the universe to accelerate. In its simplest form, dark energy is considered to have a constant energy density, meaning that as space expands, the total amount of dark energy in the universe remains the same. This is known as the cosmological constant, a concept introduced by Albert Einstein in 1927 as part of his theory of general relativity. Though Einstein originally introduced the cosmological constant to maintain a static universe, he later discarded it, calling it his biggest blunder. Today, the cosmological constant has been revived as a possible explanation for dark energy, but its true nature remains elusive. One of the most fascinating aspects of dark energy is the potential relationship between it and the quantum vacuum. In quantum field theory, the vacuum is not empty space, but instead is a seething sea of fluctuating fields and particles. These fluctuations create a kind of background energy that is thought to be responsible for the properties of space itself. Some theorists suggest that dark energy could be a manifestation of this quantum vacuum energy, an invisible energy that permeates all of space. If this is the case, then dark energy may not be a mysterious force that was created after the Big Bang, but rather an inherent feature of space itself, arising from the quantum fluctuations that occur even in the emptiest of regions. This connection between dark energy and the quantum vacuum was explored by physicists like Steven Weinberg, who proposed that the energy of the vacuum could play a crucial role in shaping the expansion of the universe. According to this idea, the vacuum energy could be responsible for the accelerated expansion of space. As the universe continues to expand, the energy of the vacuum remains constant, pushing galaxies farther apart. This theory could help explain the observed acceleration, but it also raises questions about the true nature of the quantum vacuum and whether it could have any deeper connection to the fundamental forces of nature. As scientists continue to investigate dark energy and dark matter, new theories are emerging to help us better understand the cosmos. One area of research involves studying the relationship between dark matter and dark energy. Could these two invisible forces be related in some way, perhaps through their interactions with the quantum vacuum? Some theorists believe that dark matter and dark energy could be two sides of the same coin, interacting in ways we do not yet understand. In this view, dark matter could be the gravitational counterpart to dark energy, while dark energy could be the driving force behind the expansion of the universe. Understanding this relationship could unlock key insights into the universe's structure and its ultimate fate. Even as we continue to probe the mysteries of dark matter and dark energy, one thing is clear. These invisible forces are crucial to the evolution of the universe. They shape the cosmos at the larger scales, dictating the formation of galaxies, stars, and clusters, and driving the accelerated expansion of space. Though we still don't know exactly what dark matter and dark energy are, their discovery has opened up entirely new realms of scientific inquiry. As we continue to explore the universe, these forces will remain at the forefront of our quest for knowledge, guiding us toward a deeper understanding of the very fabric of reality. As we look up at the night sky, we see a vast, ever-expanding universe, a universe that, according to modern cosmology, is still unfolding. But while the cosmos may seem infinite to us, it is not immune to the passage of time. The universe, like all things, has a fate, and how it will end is a subject of great intrigue and scientific speculation. The end of the universe is not a singular, straightforward event, but rather a range of possible scenarios, each shaped by different factors like dark energy, gravity, and the expansion of space itself. One of the most widely discussed theories of the universe's ultimate fate is the Big Freeze or heat death scenario. This theory suggests that the universe will continue to expand forever, gradually cooling down as galaxies move farther apart. The idea is based on the observation that the expansion of the universe is accelerating, driven by a mysterious force known as dark energy. As space stretches, the universe's temperature will drop and stars will burn out. The result will be a cold, dark, and empty cosmos, with no stars, no galaxies, and no new generations of cosmic objects forming. Over an unimaginable timescale, the universe will reach a state of maximum entropy, where all energy is evenly spread out and no more useful work can be done. This is what is referred to as the heat death of the universe, a state where everything is in equilibrium and no further change is possible. The concept of the Big Freeze was explored in detail by cosmologists such as Sean Carroll and Max Tegmark. Carroll, in his work on the fate of the cosmos, explains that the acceleration of the universe's expansion, driven by dark energy, makes this scenario the most likely outcome. As galaxies move farther apart and stars run out of fuel, the universe will become increasingly desolate. There will be no new stars to form, no stellar systems to thrive, and the universe will be left in a state of darkness and coldness. This scenario raises profound questions about the nature of time and change in the universe. If everything eventually becomes uniform and inactive, is there an ultimate purpose or meaning to the cosmos, or is it simply an endless cycle of birth, life, and death? Yet, the Big Freeze is not the only possible fate for the universe. Another intriguing theory is the Big Rip, a scenario in which dark energy causes the universe's expansion to accelerate indefinitely. Unlike the Big Freeze, which envisions a gradual cooling of the universe, the Big Rip suggests that the very fabric of space-time itself will eventually tear apart. In this scenario, as dark energy grows stronger, galaxies, stars, and even the fundamental building blocks of matter, atoms and subatomic particles, will be pulled apart by the relentless stretching of space. The Big Rip would occur over a timescale of billions of years, but as dark energy accelerates its influence, the cosmic expansion would become increasingly dramatic. At first, galaxies would be separated from each other at increasing speeds, and then individual stars and solar systems would begin to break apart as the force of expansion overcomes the gravitational pull that binds them together. Eventually, even the atoms that make up matter would be torn apart, as the repulsive force of dark energy overcomes the electromagnetic forces holding atoms together. The Big Rip presents a vision of cosmic destruction, where not only the galaxies and stars are erased, but the very building blocks of matter are scattered into nothingness. This dramatic scenario is still speculative, but it highlights the complex and unpredictable ways in which dark energy could shape the future of the universe. The Big Rip is a theory that directly contrasts with the notion of the Big Freeze, yet both are rooted in the same observation. The expansion of the universe is accelerating. This raises the question of whether dark energy is a constant force, or if it could evolve over time in ways we don't yet understand. The potential for either a Big Freeze or a Big Rip brings to light the role that dark energy plays in the overall dynamics of the universe, and how it could ultimately determine the universe's fate. However, there's a third possibility, one that suggests the universe may not have a definite end at all, but rather a cyclical pattern of expansion and contraction. This is the theory of the Big Crunch, which proposes that, rather than expanding forever, the universe will eventually stop expanding and begin to contract. Gravity, which today holds galaxies and stars together, would begin to dominate, pulling everything back toward a single point, a singularity, where all matter and energy are compressed. The Big Crunch would be the universe's ultimate collapse, where time and space as we know them would cease to exist. The Big Crunch is reminiscent of the conditions thought to have existed before the Big Bang. Just as the universe emerged from an incredibly dense and hot state, so too would it return to a state of extreme density and heat. This idea has been explored by physicist Roger Penrose, who proposed that the universe could undergo infinite cycles of expansion and contraction. According to Penrose's conformal cyclic cosmology theory, each Big Bang is the start of a new cycle, and the Big Crunch could mark the end of one cycle, only for a new universe to emerge from the remnants of the previous one. This theory suggests that the universe is part of an eternal cycle, with each Big Bang and Big Crunch representing a moment of cosmic rebirth. While the Big Crunch remains an intriguing possibility, current evidence suggests that it is less likely than the Big Freeze or the Big Rip. Observations of the universe's accelerated expansion, driven by dark energy, point to a future where expansion continues indefinitely, rather than slowing down enough to reverse itself. However, the cyclic model, as proposed by Penrose and further developed by cosmologists like Paul Steinhardt and Neil Turok, continues to offer a fascinating alternative to the idea of a one-time Big Bang followed by an ultimate end. In the cyclic model, the universe's evolution is not a linear progression from birth to death, but rather a series of rebirths, with each cycle bringing about a new universe from the ashes of the old. The implications of these ideas stretch beyond the physical universe. If the universe is indeed cyclical, then the concepts of beginning and end lose some of their meaning. Time might not be a straight line moving from past to future, but rather a loop that continually regenerates itself. This raises profound questions about the nature of existence itself. What does it mean for something to begin if it has no true start? And if the universe is constantly being reborn, what does that suggest about the meaning of our own existence within it? These philosophical implications take us into deep territory, where the lines between science, metaphysics, and human consciousness blur. In considering the universe's potential end, we are also confronted with the role of human consciousness in the cosmos. If the universe does indeed end in a big freeze, big rip, or even a big crunch, what does this mean for our place in it? Does the ultimate fate of the universe imply anything about our significance or the purpose of life itself? Is there meaning to be found in the vastness of time, or is the universe simply a random, ever-expanding series of events? These are questions that stretch beyond the realm of science, delving into the philosophical and existential domains. Yet, the more we learn about the universe, the more we realize how closely our understanding of the cosmos is intertwined with our own search for meaning. As we continue to study the forces that govern the universe, from dark energy to gravity to the quantum mechanics that shape the fabric of space-time, we come closer to answering these profound questions. The future of the universe may still be uncertain, but one thing is clear: it will continue to evolve in ways that challenge our deepest conceptions of time, space, and existence. Whether the universe ends in an eternal freeze, a dramatic rip, or an endless cycle of rebirths, its fate will remain one of the greatest mysteries we seek to unravel. And in doing so, we may come to understand not only the cosmos, but our place within it, both in time and beyond it. The search for life beyond Earth is one of the most profound and exciting endeavors in science. The question of whether we are alone in the cosmos has intrigued humanity for centuries, and with every new discovery, the possibility of life elsewhere becomes more tantalizing. But before we can understand where life might exist, we first need to explore how life could have formed in the universe, from the very building blocks of matter to the conditions necessary for life as we know it. The early universe was a hot and chaotic place, but it was also a crucible for the formation of the elements that are essential for life. After the Big Bang, the universe cooled down, and particles began to combine to form the simplest elements: hydrogen, helium, and trace amounts of lithium. These elements were the raw materials for everything that would come later, including the carbon-based life we're familiar with. The next phase of the universe's evolution involved the formation of stars, which acted as factories for creating the heavier elements necessary for life. In the cores of stars, nuclear fusion occurs, where lighter elements like hydrogen fuse together to form heavier elements such as carbon, oxygen, and nitrogen. These elements are essential for the chemistry of life as we know it. Carbon, for example, is the backbone of all known life forms, forming the complex molecules required for life processes. Oxygen and nitrogen are also crucial, with oxygen playing a key role in respiration and nitrogen forming part of the genetic material in DNA. As stars go through their life cycles, some explode in dramatic events known as supernovae. These explosions are responsible for dispersing these life-essential elements into the surrounding space, enriching the interstellar medium with the building blocks of life. These elements then find their way into new stars, planets, and potentially living organisms. This cycle of starbirth, death, and rebirth is how the elements that are crucial for life on Earth were spread throughout the universe. But having the right elements is only part of the equation. For life to form, there must also be the right conditions, a place where these elements can interact in the right ways. One of the most important factors for life is the presence of liquid water. Water is a solvent that can dissolve a wide range of substances, allowing for the chemical reactions necessary for life to occur. On Earth, water is found in abundance, but elsewhere in the universe, liquid water might be rare. That's why astronomers are particularly interested in finding planets that exist in what is known as the habitable zone. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on the surface of a planet, not too hot and not too cold. If a planet is too close to its star, the heat will cause water to evaporate. If it's too far away, the water will freeze. But in the habitable zone, temperatures are just right for water to remain liquid and for life to thrive. This zone is crucial for identifying planets where life could potentially exist. One of the most exciting aspects of astrobiology, the study of life in the universe, is the search for exoplanets, planets that orbit stars outside our solar system. Thanks to missions like NASA's Kepler Space Telescope, we have discovered thousands of exoplanets, and many of them lie in their star's habitable zone. Some of these planets may be similar to Earth, with the right combination of elements and conditions for life to exist. In fact, astronomers have identified exoplanets that seem to have the potential for liquid water, sparking debates about whether life might be out there waiting to be discovered. But how can we detect life on these distant planets? The first step is identifying planets that could harbour life by looking for signs of water and the right chemical ingredients. One of the tools that scientists use to do this is spectroscopy. By studying the light that passes through a planet's atmosphere, astronomers can detect the chemical composition of that atmosphere. Certain gases such as oxygen, methane, and carbon dioxide can be signs of biological processes because they are often produced by living organisms. In this way, astronomers can search for biosignatures, indicators that life might be present on planets light years away. Another important focus of the search for life is our own solar system, particularly Mars, which has long been a prime candidate for the existence of past or present life. Evidence suggests that Mars once had liquid water on its surface, and it may have had conditions suitable for life in its ancient past. Recent missions to Mars, including NASA's Perseverance rover and the Curiosity rover, have been investigating the planet's geology and searching for signs of ancient life. These missions have found evidence of ancient riverbeds, minerals that form in the presence of water, and even organic molecules which are the building blocks of life. While no definitive signs of life have been found yet, the search continues, and scientists remain hopeful that future discoveries will shed light on whether life ever existed on Mars, or whether it still might. The search for life doesn't stop with Mars, though. The outer moons of Jupiter and Saturn, such as Europa and Enceladus, also show promise as places where life could exist. Both moons have vast oceans beneath their icy surfaces, and recent observations suggest that these oceans may be in contact with rocky material, which could provide the necessary chemical ingredients for life. In the coming decades, missions like NASA's Europa Clipper will explore these moons in detail, offering a closer look at their potential to support life. As we search for life beyond Earth, the connection between cosmic evolution and the emergence of life becomes more apparent. The process that started with the Big Bang, where the simplest elements were created and dispersed throughout the universe, eventually led to the formation of stars, galaxies, and planets that could support life. The same forces that shaped the structure of the universe, from the birth of galaxies to the creation of heavy elements in supernovae, are also the forces that make life possible. While the search for life beyond Earth continues, it also brings us to deeper philosophical questions. If life exists elsewhere in the universe, what does that mean for our understanding of life on Earth? Are we truly unique, or is life a natural consequence of the right conditions? The discovery of life elsewhere could have profound implications not just for science, but for our understanding of our place in the cosmos. In the end, the search for life is not just about finding other living organisms. It's about understanding the processes that gave rise to life in the first place, and how those processes may have unfolded on other worlds. Whether we find life on Mars, on a distant exoplanet, or even in the subsurface oceans of icy moons, the search will continue to deepen our connection to the universe and to the fundamental questions about what it means to be alive in this vast cosmos. As we push the boundaries of exploration and discovery, one thing is certain: the journey to find life, whether on Earth or beyond, is one of the greatest adventures humanity has ever undertaken. At the heart of modern physics lies a concept that seems almost too strange to be true: quantum entanglement. This phenomenon, first discussed by Albert Einstein in the 1920s, has since become one of the most perplexing and intriguing aspects of quantum mechanics. Quantum entanglement refers to the idea that two particles can become linked in such a way that the state of one particle instantly affects the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, defied conventional notions of how the universe should behave. Einstein's concerns about entanglement were rooted in the belief that the universe should follow local realism, where objects only interact with their immediate surroundings, and that influences cannot travel faster than the speed of light. But quantum mechanics upends these ideas. When two particles become entangled, their properties are intertwined in such a way that measuring one particle's state immediately reveals information about the other particle, regardless of the distance between them. This was initially a puzzling idea, and for a long time physicists debated whether it could even be true. In the 1960s, British physicist John Bell developed what is known as Bell's theorem, which provided a way to test whether quantum mechanics could be reconciled with local realism. Bell's work showed that if quantum entanglement is real, then the universe cannot follow the rules of classical physics that Einstein favoured. Numerous experiments since then have confirmed the predictions of quantum mechanics, demonstrating that entanglement is not just a theoretical curiosity, but a real and fundamental aspect of nature. Now, what does all of this have to do with the cosmos on a grand scale? Well, quantum entanglement could potentially provide a link between the microscopic world of quantum mechanics and the macroscopic world of cosmology. In the early moments of the universe, when everything was compressed into a tiny, hot and dense state, the laws of quantum mechanics ruled supreme. At this point, quantum entanglement may have played a crucial role in the very formation of the universe. One intriguing possibility is that quantum entanglement could have been involved in shaping the initial conditions of the universe, especially during the period known as inflation. Inflation, as proposed by Alan Guth in the 1980s, is the idea that the universe underwent an incredibly rapid expansion immediately after the Big Bang. During this time, quantum fluctuations, small, random variations in the fabric of space-time, could have been stretched to enormous scales, setting the stage for the large-scale structure of the universe we see today. These quantum fluctuations could have been entangled, meaning that the properties of one region of space could have been linked to the properties of another region, no matter how distant they were from one another. This could explain how the universe became so homogeneous and isotropic, as regions that were once causally disconnected became entangled and shared information that ensured they evolved in similar ways. Physicist David Bohm, in his interpretation of quantum mechanics, took the idea of entanglement even further with his concept of non-locality. Bohm proposed that the entire universe is interconnected, and that particles are not separate, independent objects, but rather part of an intricate underlying whole. According to Bohm's theory, quantum entanglement is not just a peculiar feature of individual particles, but a reflection of the deep non-local connections that exist throughout all of space. This idea suggests that, at a fundamental level, the universe might not be as separate and distinct as we perceive it. Instead, everything could be fundamentally connected through a network of entangled relationships, extending across vast distances. Bohm's theory of non-locality challenges the conventional understanding of the universe, suggesting that information and influence can travel instantaneously, bypassing the limitations of space and time. If Bohm is right, quantum entanglement could have played a central role in shaping the very fabric of the universe, connecting distant regions of space and ensuring that they evolved in concert. This interconnectedness may have been crucial for the uniformity of the cosmos, particularly during the early moments when the universe was in a hot, dense state, and quantum effects were dominant. Looking beyond the early universe, quantum entanglement might continue to shape the cosmos in ways we don't yet fully understand. As the universe expands and structures like galaxies, stars, and planets form, entanglement could influence the behavior of particles and fields on a cosmic scale. In fact, there are ongoing experiments and theories that suggest quantum entanglement may have an important role to play in the large-scale behavior of the universe, even in the context of dark matter and dark energy. Could entanglement be linked to the mysterious forces that are driving the universe's accelerated expansion? Some physicists speculate that the entanglement of distant regions of space might be responsible for the effects we attribute to dark energy, suggesting that quantum processes may be at the heart of the universe's large-scale behavior. As we continue to explore the role of quantum entanglement in the evolution of the cosmos, we also encounter profound questions about the nature of reality itself. If entanglement truly links all parts of the universe, what does that mean for our understanding of space and time? Could it be that space-time, as we experience it, is an emergent property, something that arises from the deeper entangled connections between particles and fields? The implications of this idea are far-reaching, suggesting that space-time itself might not be as fundamental as we once thought. One of the most exciting prospects in modern cosmology is the possibility that quantum entanglement could help bridge the gap between quantum mechanics and general relativity, the two pillars of modern physics that, until now, have remained largely separate. While quantum mechanics governs the behavior of particles at the smallest scales, and general relativity describes the behavior of large objects like planets and galaxies, the two theories are not easily reconciled. However, if quantum entanglement is indeed a universal, non-local feature of nature, it might provide the key to unifying these two theories, allowing us to understand how gravity and quantum mechanics work together at the deepest level. As we continue to develop new experimental techniques and mathematical frameworks, we may one day be able to test these ideas more directly. For now, the role of quantum entanglement in the cosmos remains a tantalizing mystery, one that challenges our understanding of space, time, and the very fabric of reality. The search to understand how entanglement influences cosmic evolution is not just about answering questions about the past, but also about unlocking the future of cosmological research and expanding our understanding of the universe. In many ways, quantum entanglement is more than just a concept from the world of tiny particles. It's a window into the deep connections that link all things in the cosmos, from the smallest quantum fluctuations to the largest structures in the universe. The more we learn about entanglement, the more we realize that the universe might be far more interconnected than we ever imagined, an intricate web of relationships stretching across space and time. The future of cosmology, it seems, may depend on understanding the profound implications of this strange and beautiful phenomenon. Dark matter is one of the most intriguing and elusive phenomena in the universe. While it remains invisible and undetectable through traditional means, such as light, heat, or radiation, we know it must exist due to its profound influence on the cosmos. In fact, dark matter plays a crucial role in shaping the structure of the universe, particularly in the formation of galaxies. Let's rewind to the 1970s, when one of the most important discoveries in cosmology was made. Vera Rubin, an astronomer whose work would eventually change our understanding of galaxies, observed something unexpected about the rotation curves of galaxies. When astronomers observe how galaxies rotate, they expect that stars located further from the center of the galaxy would orbit more slowly, as the gravitational pull from the galaxy's mass would weaken with distance. However, Rubin's data showed that stars at the outer edges of galaxies were moving at the same speed, or even faster, than stars closer to the center. This was a major puzzle, because based on visible matter alone, such as stars and gas, there wasn't enough mass in these galaxies to explain the high rotational speeds. The only explanation, Rubin concluded, was that there was additional, unseen mass exerting gravitational influence on the stars in these galaxies. This mass, which did not emit light or radiation, would come to be known as dark matter. Rubin's observations were groundbreaking, providing the first clear evidence that most of the mass in galaxies was invisible to us. This discovery prompted a wave of new questions about the nature of dark matter, and how it might be shaping the formation and evolution of galaxies across the universe. Since then, scientists have built on Rubin's work, developing theories about how dark matter influences galaxy formation. In the early universe, just after the Big Bang, matter was distributed more or less evenly across the cosmos. But as the universe expanded and cooled, tiny fluctuations in the density of matter began to grow. These fluctuations created the seeds for larger structures like galaxies. However, gravity alone couldn't have created galaxies from such tiny seeds. Something else had to be pulling matter together, accelerating the process. This is where dark matter comes in. The gravity from dark matter could have provided the extra push needed to start clumping matter together, eventually leading to the formation of galaxies. Dark matter's role in galaxy formation is also tied to its ability to act as a sort of cosmic scaffolding. Imagine a web of invisible threads stretching across the universe, connecting regions of matter that would otherwise be too far apart to interact. This cosmic web of dark matter acts as a framework, pulling matter into galaxies and holding them together over billions of years. Without the gravitational pull of dark matter, galaxies would not have formed the way they did. Instead, the universe would likely be much more sparse, with matter scattered too far apart for galaxies to form in the dense organized structures we observe today. But what exactly is dark matter made of? That's a question that remains unanswered, but there are a few leading candidates. The most popular candidate for dark matter is a type of particle called WIMPs, which stands for weakly interacting massive particles. WIMPs are thought to be much heavier than the particles that make up normal matter, such as protons and neutrons, but they interact very weakly with ordinary matter. Because WIMPs don't interact through the electromagnetic force, which is how light is emitted, absorbed or reflected, they don't produce any detectable radiation, making them completely invisible to our eyes. If WIMPs exist, they could make up the dark matter that exerts gravitational influence on galaxies and clusters of galaxies. However, there are other theories as well. Some scientists propose that dark matter could be made of more exotic particles, such as axions or sterile neutrinos. Axions, for example, are hypothetical particles that were originally proposed to solve a problem in particle physics known as the strong CP problem. These particles are incredibly light, and if they exist, they could account for some or all of the dark matter in the universe. Sterile neutrinos, on the other hand, are a hypothetical type of neutrino that does not interact via the weak force, making them extremely difficult to detect. These particles are also considered as potential candidates for dark matter, and experiments are underway to try and detect them. While the search for dark matter particles is ongoing, scientists have come up with creative ways to study its effects indirectly. One of the most exciting techniques is gravitational lensing. Gravitational lensing occurs when light from a distant object, like a galaxy or star, is bent around a massive object, such as a galaxy cluster, on its way to Earth. This bending of light, caused by the gravitational pull of dark matter and visible matter, acts like a cosmic magnifying glass, allowing astronomers to observe distant objects that would otherwise be too faint to see. By studying gravitational lensing, astronomers can map the distribution of dark matter in galaxy clusters. Even though dark matter doesn't emit light, it exerts gravitational influence on surrounding matter, bending light in ways that reveal its location. This has allowed scientists to create detailed maps of dark matter's presence in galaxy clusters, providing strong evidence for its existence and showing how it shapes the large-scale structure of the universe. Dark matter also plays a role in the formation of larger cosmic structures, such as galaxy clusters. Galaxy clusters are massive groups of galaxies held together by gravity, and dark matter makes up a significant portion of the mass in these clusters. By studying the motion of galaxies within these clusters, scientists can estimate how much dark matter is present and how it influences the dynamics of the cluster as a whole. This helps to paint a more complete picture of how galaxies form and evolve over cosmic time. Despite all the evidence supporting the existence of dark matter, its exact nature remains one of the greatest unsolved mysteries in modern science. What we do know is that dark matter is not just a theoretical concept, it has a real, observable effect on the universe. From its gravitational influence on galaxy rotation to its role in the formation of large-scale cosmic structures, dark matter is an invisible yet indispensable component of the universe. As our technology improves, new experiments and observational techniques will continue to shed light on the nature of dark matter. Whether through direct detection of particles, more precise mapping of gravitational lensing, or the study of galaxy clusters, we are getting closer to understanding the true nature of this elusive force. Ultimately, uncovering the mystery of dark matter will not only help us understand how galaxies form and evolve, but it could also unlock new insights into the fundamental laws of the universe itself. The search for dark matter is, in many ways, the search for a deeper understanding of the cosmos, an invisible thread that connects everything we see and everything we don't. Imagine that everything we know about the universe, from the stars in the sky to the very fabric of space-time itself, is not as it seems. What if, instead of being a vast three-dimensional expanse, the universe is actually a projection from a lower dimensional space? This is the essence of the holographic principle, a mind-bending idea that challenges everything we think we know about the nature of reality. The holographic principle was first proposed in the 1990s by physicists Gerard 't Hooft and Leonard Susskind, and it suggests that the universe we experience, with its 3 dimensions of space and 1 of time, might be a kind of illusion. According to this principle, all of the information that makes up our universe could be encoded on a 2-dimensional surface, much like a hologram. In a hologram, 3-dimensional images are projected from a 2-dimensional surface, and in the case of the universe, this idea proposes that everything we see, everything we experience as 3-dimensional, could be the result of information stored on a distant two-dimensional boundary. To understand this concept more clearly, consider a black hole. When matter falls into a black hole, it's often described as being lost forever, as the gravitational pull is so strong that not even light can escape. However, in the early 1970s, physicist Stephen Hawking introduced a problem that would later become known as the black hole information paradox. According to quantum mechanics, information cannot be destroyed, but black holes seem to destroy it by pulling everything inside and trapping it behind an event horizon. This created a fundamental conflict between the laws of quantum mechanics and the behavior of black holes. Hawking's work on black holes eventually led to the development of the holographic principle. In particular, the principle provided a potential resolution to the information paradox. The idea is that the information about everything that falls into a black hole is not lost, but instead is encoded on the two-dimensional surface of the event horizon, the boundary of the black hole. This information would then be projected into the three-dimensional space inside the black hole, much like a hologram. In this way, the holographic principle offers a solution to the paradox, suggesting that information about the interior of a black hole could be preserved on its boundary in a lower dimensional space. This insight has profound implications for our understanding of spacetime itself. If the holographic principle is correct, it could mean that the very nature of the universe as we experience it is not what it seems. Instead of being a fully three-dimensional structure, spacetime could be the projection of something far more fundamental, existing in a lower dimension. This could radically change how we think about the fabric of the universe and might offer a new framework for understanding gravity, quantum mechanics, and even the nature of time itself. One of the most exciting possibilities offered by the holographic principle is its potential to unify the two great pillars of modern physics: general relativity and quantum mechanics. General relativity describes the force of gravity, which governs the large-scale behavior of the universe, from planets and stars to galaxies and black holes. Quantum mechanics, on the other hand, describes the behavior of the smallest particles of the universe, like electrons and photons. However, the two theories are incompatible when it comes to the extreme conditions inside black holes or during the Big Bang, where both gravity and quantum effects are at play. The holographic principle could offer a way to bridge this gap, suggesting that spacetime itself might be a quantum phenomenon, and that our three-dimensional universe could be an emergent property of a deeper, more fundamental structure. The holographic principle also raises intriguing questions about the nature of the Big Bang and the origins of the universe. If the universe is a projection, what does this say about its birth? Could the Big Bang itself be the result of a transition from a lower dimensional space to the higher dimensional universe we experience today? Some theories suggest that our universe may have originated from a higher dimensional bulk, and that the Big Bang was the moment when this lower dimensional information was projected into our three-dimensional space. This would mean that the very act of the Big Bang, the creation of the universe, might have been a holographic event, where the information that defines our cosmos was encoded and projected into existence. The implications of the holographic principle extend beyond just black holes and the Big Bang. It also offers new perspectives on the nature of dark matter and dark energy, the mysterious forces that seem to dominate the universe's behavior. Since both dark matter and dark energy have yet to be directly detected, they remain one of the greatest mysteries in cosmology. However, if the universe is a hologram, it's possible that the effects of dark matter and dark energy are not caused by unseen particles or forces, but by the way information is encoded in the fabric of spacetime itself. This could mean that dark matter and dark energy are not fundamental substances, but rather emergent phenomena, arising from the properties of the lower dimensional space from which our universe is projected. While the holographic principle remains speculative, it has already had a profound impact on the way we think about the universe. It provides a framework for understanding the universe in terms of information rather than matter and energy, which could lead to new insights into the fundamental nature of reality. One of the most exciting aspects of the holographic principle is its potential to resolve some of the deepest questions in physics, such as the nature of black holes, the unification of quantum mechanics and general relativity, and the origin of the cosmos itself. In the coming years, new experiments and observations may help to test the validity of the holographic principle. One of the ways scientists hope to do this is through the study of black holes and the cosmic microwave background radiation, the faint afterglow of the Big Bang. By studying the way information is encoded in these phenomena, Scientists may be able to gather indirect evidence for the holographic nature of the universe. Additionally, advances in string theory and quantum gravity may provide further insights into how spacetime behaves at the most fundamental level, potentially confirming or refuting the holographic model. As we continue to explore the cosmos, the holographic principle challenges us to think in new and profound ways about the universe. It suggests that everything we experience, the stars, the galaxies, even space and time itself, might be the result of a projection from a deeper hidden reality. If true, this could change not only our understanding of the universe, but also the way we think about ourselves, our place in the cosmos, and the very nature of existence. One of the greatest challenges in modern physics is unifying two of its most successful theories: general relativity, which describes the force of gravity on large scales, and quantum mechanics, which governs the behavior of particles at the smaller scales. Both theories have been incredibly successful in their respective domains. General relativity provides our understanding of massive objects like planets, stars, and black holes, while quantum mechanics explains the strange and fascinating world of particles and forces at the atomic and subatomic level. However, the two theories are fundamentally incompatible when it comes to the extremes of space and time, such as the environment inside black holes or during the first moments of the Big Bang. This incompatibility has led to the search for a theory of quantum gravity, one that can reconcile gravity with the principles of quantum mechanics and provide a unified framework for understanding the universe at all scales. The quest for quantum gravity is, in many ways, the holy grail of modern physics. It would not only explain the behavior of space-time at the smaller scales, but could also shed light on some of the most profound mysteries of the cosmos, such as the nature of black holes, the Big Bang, and the very fabric of reality itself. Over the past several decades, physicists have proposed various approaches to this grand unification, two of the most prominent being loop quantum gravity and string theory. Loop quantum gravity, developed by scientists like Carlo Rovelli and Lee Smolin, is an attempt to quantize gravity directly without relying on higher dimensions or new particles. It builds on the framework of general relativity, which describes space-time as a smooth, continuous fabric, and combines it with quantum mechanics, which describes particles and fields as discrete and quantized. In loop quantum gravity, space-time is thought to be composed of tiny, discrete units, or loops, which form the fabric of the universe at the smallest scales. These loops are not points or particles, but rather a network of interconnected spins, and they are responsible for the geometry of space-time. The key idea behind loop quantum gravity is that, at the Planck scale, the incredibly small scale at which both quantum mechanics and gravity are important, the smooth fabric of space-time breaks down into discrete units. These units would form a kind of quantum foam, where the geometry of space-time fluctuates in random ways. This view of space-time as quantized could help resolve some of the paradoxes associated with black holes, such as the loss of information, and may provide a deeper understanding of the early universe. One of the most intriguing aspects of loop quantum gravity is its potential to explain the Big Bang without a singularity, a point where all matter is compressed into an infinitely small space, which currently leads to the breakdown of the laws of physics. In loop quantum gravity, the universe might have undergone a bounce, where a previous universe collapsed in on itself, and the current universe emerged from the remnants of that collapse. This approach offers a way of avoiding the singularity problem, and suggests a potentially cyclical model of the universe. However, loop quantum gravity has yet to provide definitive answers to some of the biggest questions in physics, and there are still many open problems to resolve. For example, the theory does not yet explain how quantum mechanics and general relativity should be combined at the larger scales, or how it fits with the observed effects of dark matter and dark energy. While loop quantum gravity remains a promising and mathematically rigorous approach, it is far from a complete theory of quantum gravity. This brings us to another approach to unifying general relativity and quantum mechanics: string theory. String theory, developed by physicists such as Leonard Susskind, Edward Witten, and others, proposes that the fundamental building blocks of the universe are not point-like particles but tiny vibrating strings. These strings can vibrate in different modes, and the different vibrational patterns correspond to the different particles and forces we observe. Unlike loop quantum gravity, which quantizes gravity directly, string theory aims to describe all of the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces within a single framework. One of the most important aspects of string theory is that it requires extra dimensions of space beyond the three we are familiar with. In order for string theory to work, the universe must have a total of 10 dimensions, 9 spatial dimensions and 1 time dimension. These extra dimensions are thought to be compactified, or curled up, at incredibly small scales, which is why we don't experience them directly in our everyday lives. The existence of these extra dimensions has profound implications for the structure of the universe and how the forces of nature operate at the most fundamental level. For example, string theory allows for the possibility of new, exotic particles and forces, some of which could help explain phenomena like dark matter and dark energy. String theory also provides a framework for understanding the very early moments of the universe. During the Big Bang, when the universe was in an extremely hot and dense state, quantum fluctuations would have been far more significant than they are today. String theory suggests that the universe could have started from a quantum foam of vibrating strings, with space-time itself emerging from these fluctuations. This view could provide new insights into the nature of the Planck era, the first fraction of a second after the Big Bang, when the universe was incredibly small and dense, and quantum effects dominated. String theory's focus on the quantum properties of space-time might also provide a way to explain the origin of the universe, offering a unified framework for understanding both the smallest and the largest scales of nature. Despite its elegant mathematical structure, string theory faces challenges in making predictions that can be tested experimentally. Unlike loop quantum gravity, which can be studied through mathematical models of space-time, string theory relies on extra dimensions and higher-order calculations that are difficult to observe or measure directly. However, string theory has led to new insights in fields like black hole thermodynamics, and has suggested ways to resolve paradoxes like the black hole information paradox. Additionally, the study of string theory has spurred new developments in areas like quantum field theory, particle physics, and cosmology, even if its full implications for the nature of gravity are still unfolding. The search for quantum gravity also involves new and innovative ways of testing the theory. One of the most promising avenues for experimentation is the detection of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects, like merging black holes or neutron stars. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, confirming a major prediction of general relativity. These waves provide a unique way of studying the very fabric of space-time itself, and could offer clues about how quantum gravity works at the larger scales. Future experiments such as the proposed LISA, Laser Interferometer Space Antenna, mission aim to detect gravitational waves from even more distant and powerful cosmic events, potentially providing new insights into the quantum nature of gravity. As we continue to probe the mysteries of the universe, the search for quantum gravity remains one of the most exciting and challenging areas of research. Whether through loop quantum gravity, string theory, or other approaches, unifying quantum mechanics and general relativity holds the promise of revolutionizing our understanding of space, time, and the very nature of the cosmos. The discoveries made in this field could not only unlock the secrets of the universe's beginnings, but also reveal new dimensions of reality, bringing us closer to a complete theory of everything, a framework that describes all the forces of nature and the origin of the cosmos itself. The search is still ongoing, but the possibilities are boundless. The universe, as we observe it, is fine-tuned in such a way that life is not only possible but abundant. The very fact that we exist with all our complexities may seem to be a coincidence, but the anthropic principle suggests that this coincidence is deeply connected to the nature of the cosmos itself. According to the anthropic principle, the universe is in some way designed or conditioned to allow life to emerge, suggesting that the universe's physical constants, such as the strength of gravity, the charge of the electron, or the mass of the proton, are precisely tuned for the existence of life as we know it. The idea of the anthropic principle was first formally articulated by cosmologist Brandon Carter in the 1970s. Carter proposed that the physical constants and laws of the universe must fall within a very narrow range for life to arise. If any of these constants were even slightly different, life would not be possible. For example, if the strong nuclear force which holds atomic nuclei together were just a little weaker or stronger, atoms could not form in the way they do, and the chemistry necessary for life would not exist. Similarly, if gravity was stronger or weaker, stars would burn too hot or too cold to support the complex processes needed for life to develop. The fine-tuning of the universe is not limited to just one constant or property. In fact, there are many factors, such as the ratio of the electromagnetic force to gravity, or the density of dark energy, that must fall within very specific ranges to allow for the emergence of life. This observation has led many to wonder, why is the universe so precisely fine-tuned? Could there be a deeper explanation for this apparent coincidence? One possible answer comes from the idea of multiple universes, or the multiverse. According to this view, our universe is just one of many, each with different physical constants. The multiverse theory, proposed by physicists like Hugh Everett and David Deutsch, suggests that there are countless universes, each with its own set of physical laws and constants. Some of these universes may have conditions that are completely inhospitable to life, while others may be finely tuned for the emergence of life, like ours. In the context of the multiverse, the fine-tuning of our universe is not so surprising. If there are an infinite number of universes, it makes sense that at least one of them would have the right conditions for life to emerge. This is sometimes called the anthropic selection argument. We find ourselves in a universe that supports life because of all the possible universes, only those with the right physical constants allow for the existence of observers like us. In other words, if life exists in our universe, it must be because the conditions are just right for it. The anthropic principle, then, is not a claim that the universe was created with life in mind, but rather that we are here because the conditions for life happen to be met. This brings us to a more profound philosophical question. What does it mean for the universe to be fine-tuned for life? Does this imply that the universe was somehow designed with purpose, or does it suggest that our existence is simply a result of statistical probability, given the vast number of universes in the multiverse? The question of whether life exists because the universe is designed, or whether it's simply the result of chance, is one that continues to spark debate among scientists, philosophers, and theologians alike. One of the most compelling aspects of the anthropic principle is that it forces us to confront the nature of life itself. If the universe is finely tuned for life, then what does that say about the universe's ultimate purpose? Some interpretations of the anthropic principle suggest that the universe, in its vastness, may exist simply to give rise to observers who can ask these questions. In this view, life becomes a necessary consequence of the structure of the universe, and the universe is not just a random collection of matter but a place where the conditions for life are essential for its very existence. This idea is similar to the argument that our consciousness is not merely an accidental byproduct of evolution but a fundamental part of the cosmic order, with a purpose yet to be fully understood. The implications of the anthropic principle also extend beyond just the fine-tuning of physical constants. If life is a natural consequence of the universe's laws, then understanding how life arises may provide new insights into the ultimate nature of the universe itself. For instance, some physicists suggest that the study of life, how it emerges, evolves, and exists in relation to the laws of physics, could offer important clues about the larger structure of the cosmos. This could open up new avenues of research in fields like cosmology, evolutionary biology, and even artificial intelligence, as we seek to understand the very principles that govern the emergence of life. However, there are significant challenges to testing the anthropic principle scientifically. By definition, we can only observe and study the universe we live in, which makes it difficult to test the idea of a multiverse, or to observe universes with different physical constants. While the idea of multiple universes remains speculative, some researchers are trying to find indirect evidence for the existence of a multiverse by looking for signs of imprints from other universes in the cosmic microwave background radiation, the afterglow of the Big Bang. These imprints could potentially be subtle patterns or anomalies that suggest the existence of other universes with different laws or properties. However, this remains a highly speculative and controversial area of research. One of the most profound aspects of the anthropic principle is that it challenges our traditional notions of the universe and our place in it. For centuries, we have thought of the universe as a vast, impersonal expanse where life is a rare and possibly accidental occurrence. But the anthropic principle suggests that the universe is not just a random collection of matter, but may, in some sense, be finely tuned to support life. This raises the possibility that life is not just a cosmic accident, but an essential part of the fabric of the universe. Whether or not this is true, the anthropic principle invites us to consider the deep connection between life, the universe, and the very laws that govern the cosmos. Ultimately, the anthropic principle invites us to think about the universe in a new light, asking us to consider whether the cosmos is simply a backdrop for our existence, or if life itself is an inherent feature of the universe's design. While we may never fully answer this question, the search for understanding the fine-tuning of the universe and the possibility of other universes continues to inspire new ideas and theories that challenge our view of reality. The exploration of this principle, whether it leads to a multiverse or to a deeper understanding of the universe's laws, is an essential part of humanity's quest to understand the cosmos and our place within it. As we reflect on the vast and intricate story of the cosmos, from the fiery birth of the Big Bang to the ongoing expansion of the universe, we are reminded of just how dynamic and ever-evolving this journey truly is. The Big Bang marks the beginning of everything we know, the formation of space, time, and matter, but it also set the stage for a cosmic odyssey that continues to unfold, full of new mysteries, revelations, and discoveries. Each step in our exploration of the universe opens new avenues of understanding, challenging our assumptions and pushing the boundaries of what we thought was possible. At the heart of this journey lies our quest to understand our place in the universe. From ancient civilizations gazing up at the stars, wondering about the cosmos, to the cutting-edge research and technologies of today, humanity has been on a relentless quest to understand the nature of the universe and our role within it. The story of the cosmos is not just one of distant stars and galaxies, it's a story of discovery, curiosity, and the desire to connect the dots between the vast reaches of space and the tiny moments of our own lives. Throughout this exploration, new theories and ideas have shaped our understanding of the universe. Concepts like dark matter, dark energy, and quantum gravity have transformed the way we think about space-time, matter, and the forces that govern the cosmos. The birth of the universe and the very fabric of reality itself have become areas of intense inquiry, with scientists exploring everything from the nature of quantum entanglement to the fine-tuning of the universe for life. These theories, though still in their infancy, have opened up new pathways for discovery, encouraging further questions and deeper insights into the universe's origin, structure, and eventual fate. And yet, despite these advancements, we have only scratched the surface. The universe is vast beyond measure, and with every new discovery, we realize just how much we still have to learn. Whether it's the mysteries of dark matter, the true nature of dark energy, or the quest to uncover the unification of quantum mechanics and gravity, there is no shortage of frontiers left to explore. As our technology improves and our theoretical models evolve, we will undoubtedly uncover new layers of the cosmic story, each one more complex and awe-inspiring than the last. But as much as we've learned, there's something humbling about the sheer scale and complexity of the universe. We live on a small planet orbiting an ordinary star in one of billions of galaxies, and yet, despite our smallness in the grand scheme of things, we have managed to unlock some of the greatest mysteries of the cosmos. This journey of exploration, whether through the study of the cosmic microwave background radiation, the detection of gravitational waves, or the search for life on distant exoplanets, reminds us of the power of human curiosity and ingenuity. The ongoing exploration of the cosmos invites us to embrace the unknown with wonder and humility. It reminds us that there is still so much to discover, so many questions left unanswered. As we continue to gaze at the stars, whether through the lens of a telescope or through the lens of our imagination, we are reminded that the universe is a vast, ever-expanding puzzle, and each discovery is another piece in the grand picture. In the end, the story of the cosmos is not just about the universe itself, it's about our journey within it. As we continue to expand our knowledge and understanding, we are continually reshaped by the mysteries we uncover. Every answer leads to new questions, and every new discovery brings us closer to understanding the very nature of existence. The journey will never be complete, for the universe is constantly evolving, as are our ideas and perceptions. But that, perhaps, is the most beautiful aspect of all. The journey is as infinite as the cosmos itself. As we continue our exploration of the universe, let us embrace the endless possibilities that lie ahead. With each step forward, we are not just discovering the universe, but discovering ourselves within it. And though the future of cosmology is filled with uncertainties, one thing is certain. The pursuit of knowledge will continue to expand as infinitely as the universe itself.